Now, okay. Someone was asking me something. Ask now.
No, sir, it's fine.
Okay.
I'm through with.
Okay. So this is the region. This is the region of the third problem. And this particular region, bounded region, is called convex polyhedron. And this particular feasible region has three corner points. One corner point is this, one corner point is this, and one corner point is this. Now we are going to substitute. Our objective function was z is equal to 5x1 minus 2x2. Okay. We are going to substitute all these corner points. We are going to substitute all these corner points in the objective function. And we'll find its value. So if I substitute 0, 0, obviously the value of the function will be 5 into 0 minus 2 into 0. And it is the 0. If I substitute half comma 0, we will get 5 into half minus 2 into 0, that is 5 by 2. And if I substitute the third one, we will get 5 into 0 minus 2 into 1/3. So the answer is minus 2/3. Now you see that the minimization type of problem we are actually dealing with. Minimization type of problem we are actually dealing with, and this in this particular problem, actually in this convex polyhedron, there are inside this region there are infinitely many points. Actually, all of these points will satisfy the constraint. You can take any point inside and you can check. You can mark one point like here. You draw it carefully, mark the coordinate, and you can check that it is satisfying the inequality also. But as I told you in the previous session, that to find the optimized value of the problem, you don't have to see what sort of we don't have to work with all the points, all the possible points, because it is not possible actually. So theorem says that you can deal only with the corner points. Okay, you don't have to think with other points. Corner points always give us the optimal solution, a minimal solution or maximum solution. So corner points, will only concentrate on the corner points. Now, if I consider these three corner points, what is the minimum value of these three?
Minus 2 by 3.
Minus 2 by 3. Minus 2 by 3. So we'll mark it minus 2 by 3. Why am I considering the minimum value? Because it is the minimization type of problem that I was considering in problem number 3. And therefore the solution of the problem will be the minimized value of z is equal to minus 2 by 3, and the corresponding value of x1 equal to 0, and the corresponding value of x2 is equal to 1/3. This is the solution of the given problem. That is the problem number 3. Now, in problem number 4, I'm going to change a little bit once again. I'm keeping the objective function as it is, denoted by z, subject to the constraint 2x1 plus 3x2 greater than or equal to 1, x1 comma x2 greater than or equal to 0. And here I am changing a little bit. Previously, I considered minimization type of problem. Now I am considering the maximization type of problem. I want to maximize the thing. Oh, sorry. This problem is already done. So here I need to consider less than inequality. So it will be 3x2 less than inequality, less than or equal to 1. Okay, so this is the problem. This is the same, the figure of the problem, the diagram for the problem will be same as the previous one. The diagram of this problem will be same as the previous one. Okay, as you can see, you already did this here. So you need to draw the figure. You need to draw the figure once again. Okay. Now, after this, you need to substitute the corner points also, and then substitute the corner points, the coordinates of the corner points in Z, in the objective function. We have already substituted it. You can see above. Okay. Now, since this problem is a maximization type of problem, what is the maximum value here?
5/2.
5/2. For this reason, the solution of the problem will be the maximum value of Z will be 5/2.
And x1 is half and x2 is 0.
And x1 is half and x2 is 0. So you see one thing, I could have taken different problems for showing you these different type of examples, but instead of doing that, I considered the same problem and I changed here and there, and I showed how, with respect to the change made in the problem, the solution, the feasible region, the solution of the problem are actually changing. So you need to be very careful while marking the region, and you have to be very careful what sort of problem you are dealing with. Is it a maximization type of problem or a minimization type of problem, or what sort of problem it is? Okay. So with these 4 examples, we have got 4 different types of solutions. Now you take the screenshot of this page. I'm going to move on to the next page. I'm going to show you another type of problem.
Sir,
Yes.
sir, attendance টা sir আগের ক্লাসেরটাতে দেওয়া হয়নি, আমি এখন দিয়ে দিয়েছি।
I'm saving. I have saved.
Okay sir, okay sir.
What is your
Thank you,
name?
sir.
What is your name?
Rashmi sir. Rashmi
okay.
Paul.
Okay. Okay, so now I'm going to consider another problem, question number 5. Here I am going to consider a problem which is of maximization type, maximize Z, which is, let us consider the objective function to be, say 2x1 plus x2, like this, subject to x1 plus x2 greater than or equal to 1, and 2x1 plus 2, okay, 2x1 plus, or I can write it, let us take something different, x1 plus x2 less than or equal to say 2. This type of problem I've chosen, and x1 and x2 greater than or equal to 0. Now suppose this is my problem. Okay, first of all, we need to draw the figure diagram. So it will draw the two axes. And let me first mark the axis first of all. This is x1 and x2. This is the origin. And in this sort of problem, we'll always consider the positive quadrant, remember. Here in this particular problem, we have now got two constraints. And for these two constraints, we need to draw two straight lines, one of which will be denoted by L1, that is line 1. And another will be denoted by L2, which is line 2. Now, first of all, we consider this line 1, which is x1 plus x2 equal to 1 in its intercept form. In intercept form, we can rewrite this equation as x1 by 1 plus x2 by 1 is equal to 1, which is same as the previous one. And therefore, we'll mark the point 1 over here. So this is the point 1 and on the x1 axis, and this is the point 1 on the x2 axis. The coordinate will mark the point as A, whose coordinate is 1, 0. We'll mark this point as B, whose coordinate is 0, 1. Okay. And we'll join them by straight line. We'll join them by straight line like this. This is my line 1, and we'll write somewhere in the figure that it is my line 1 so that we can easily understand later. So we call it as line 1. Okay. My next equation is x1 plus x2 less than or equal to 2. So we'll consider that x1 plus x2 equal to 2. This is my equation. We will try to bring it in its intercept form. So we'll divide both the sides by 2. And we will get x1 by 2 plus x2 by 2 equal to 1. And we'll mark those points over there. So we'll mark a point 2 on the x1 axis and 2 on the x2 axis. We'll call this point as C, which is having the coordinate 2, 0. And we'll call this point as D, which is having the coordinate 0, 2. We'll join them by straight line. We'll join them by straight line like this. Okay. Now, you see that to mark the region, we need to substitute 0, 0. I'm writing here to mark the region which will be common feasible region in this case, which will be common feasible region here, because we have to mark a type of region which will be satisfied by both the inequations. Okay, you have to consider such a region which is being satisfied by the inequation 1 as well as inequation 2. So such a region will be a common feasible region in this case. The previous case, since there were only one inequation, so we didn't bother about finding common feasible region because it didn't have any meaning. But now, since there are two constraints, we have to deal with the common feasible region. Okay. To find the common feasible region, we need to substitute 0, 0 in all the inequations. In all the inequations. And accordingly, we will find the common space. Common space. Now you see, if I substitute 0, 0 in the line 1, putting 0, 0 in line 1, what we get? We get something which is absurd. Something which is absurd. If I put 0, 0 in line 1, we get something which is absurd because 0, 0 doesn't satisfy line 1. Okay. So which side of the region will be the common will be the marked region for this? Which side? This side or that side?
Upper side.
Upper side. This is my line to remember. So this upper side is my marked region. This is my region. This is not the common region, but this is the region with respect to line 1. This is the region with respect to line 1. Okay, fine, no problem. Putting 0, 0 in line 2, we get the thing is being satisfied. the inequation is being satisfied. So what portion of the line 2 will be the, yes?
Lower side.
Lower side. Yes.
Lower side.
Why the shade is towards the opposite direction? The line
I told you now,
in
because
the
it is,
diagram.
yeah, it is not satisfying this equation now. 0, 0, 0 plus 0 is greater than or equal to 1. It cannot be. So the rule is, if it doesn't satisfy the inequation, marked region cannot be that side which contains 0, 0. If you mark the region on this side, that means 0, 0 is satisfying your inequation, but it is not satisfying in your inequation, and therefore it will be the opposite side. But here in the second one, it is satisfying the inequation. So the region will be that side which contains 0, 0. So I'm drawing it by some other color. This is the marked region. This is the region corresponding to line 2. This is the region corresponding to line 2.
It's the yellow line.
Yellow line. Yellow line. Yellow line corresponds to line 2, and pink line, sorry, not pink line, black
Side
line,
one.
black one. Nah. Black line corresponding,
Yes, sir.
black line corresponds to line 1.
Yellow
Okay.
one.
Line 1. Now, what is the common part? Where do they intersect? This black line and yellow line?
Between L1 and L2.
Yeah. These two lines,
Between
yeah, these two lines are actually intersecting. These two lines are actually intersecting between line 1 and line 2. Line 2. So the common feasible region is being marked in green in the figure. You can ask me that, sir, you are taking different colors to draw these regions. What can we do in the examination? In the examination, you can use any color, green, blue, black, except red, to mark this region. And I'll recommend always to use different colors to solve problems of this type. Okay, it is for the sake of your better representation. So this green colored portion is the common region, common feasible region.
Sir, we can use pen for this.
Yeah, you can use
graph.
pen. Yeah, you can use pen. You don't need to take graph paper also. You can do it just like I'm doing it on the white sheet. Okay, so red color pen you cannot use. Except red color, you can use any color, and white color also you cannot use, because you know why. Now, this green color portion is the common feasible region, and the corner points. How many corner points are there in this particular case? How many corner points?
Four.
So here, the common feasible region, the region has 4 corner points. Has 4 corner points. Corner points. What are these? A is
Sir,
equal
A,
to
C,
A10,
D, B.
10,
yeah, B01,
B0,
C20,
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 D02, and for
D02.
2. And for all of these points, you find the value of Z. Find value of Z, Z, Z. And tell me what are these values. So if I put Z, if I put 10 in the function, we'll get the value 2.
2.
If
2,
I
sir,
put
2.
01, we'll get the value 1. If I put 20,
4.
we'll get the value 4, and here we'll get the value
4.
Then 2.
2. 2.
And
So
maximize is C.
maximum is C. Yeah.
4.
4.
C is
Maximum
4.
value is 4. So this is the maximum value. This is the maximized value. This is the maximized value. So this is my solution of the given problem. This is my solution of the given problem. So this is the maximum solution. The maximum solution is 4, and the corresponding coordinates are 2, 0. The corresponding coordinates are 2, 0. This is the solution of the problem given in question number 5. Now you tell me, I'm not writing it once again. You tell me, if you have no doubt in this particular problem, tell me that if I change, suppose I'm considering another problem, question number 6, and instead of considering maximize, I'm writing minimize Z. Rest is remaining same. Minimize Z and rest is same. What will be the solution then?
Sir, I think so. B, sir.
B, exactly.
So 1, B1.
B1.
1 and x1 is 0 and x2 is 1.
Yes. So this is the,
Yes, sir.
for question number 6, not quite, this is for question number 5. This answer, those who are not understanding, for them I'm writing. This answer which I have marked is for question number 5. And this answer which I'm writing is for question number 6. Question number 6. So in this case, the minimum value is 1 and the maximum value is, minimum value is 1 and the value of x1 is 0 and value of x2 is 1. So same problem, minor change, 2 different solutions. Now I am asking you another question. Now carefully listen to me. You take a screenshot of this, or rather it would be much better if let me ask over here.
Only,
Suppose,
sir, instead of maximize, it is minimize in question 6.
yeah, in question 6 only changes that instead of writing maximize, I have written minimize.
Okay.
This is the only change. Now I am considering a question number 7, and question number 7 I'm giving you the same problem, something in different way. Question number 7, maximize Z, which was 2x1 plus x2, 2x1 plus x2, subject to x1 plus x2 less than or equal to 1, x1 plus x2 greater than or equal to 2, x1 comma x2 greater than or equal to 0. What will happen then? What will be the change? Let us try to understand this particular part. So we are drawing it x2. Here we are drawing x1. This is the origin 0, 0. This point, roughly speaking, this is your line 1, whose coordinate were, this is A10 and this is B01. And this point is, say, roughly this is 0, 2 marked by D, and this is C marked by 1, 2, 0. And this is your line 2. Just like the previous case, I have drawn the figure. Now this is the problem which is in front of you. Maximization type of problem. Tell me, help me to identify the region. Tell me what sort of region
For
will be.
line one, region will goes downwards.
Which one?
For line one.
For line one, it will be
Blue one.
blue
Yes,
one?
line one.
Which side? Which side?
Downwards.
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 Yeah.
And
Okay.
for line two, it goes upwards.
For line 2, it is upwards. Now you have understood.
Yes.
For line 2, it is upwards. Okay, like this. Now what is the common feasible region in this case?
Sir, there is no common feasible.
No common feasible region. So
There is
this particular
No
problem,
common.
yes. This particular problem has no common feasible region. No common feasible region. So this problem has infeasible solution, or we can say this problem has no solution at all. No solution at all. So one fundamental requirement for finding common a solution, a maximized value or the minimized value, is to have the common feasible region in this in LPP. If you cannot find the common feasible region, that means your solution, you will not find any solution at all. If you find a common feasible region, then probably you can find a solution. Otherwise, you will not be able to find the solution. Now, in question number 8,
Sir, common region that থাকবেই।
স্যার বলছি ওই ইকুয়েশন 1 এর জন্য তো পয়েন্টের কমন রিজিয়নের অ্যাবাভে আছে, মানে মাঝে যে হোয়াইট রিজিয়নের গ্রিন লাইনটা তো ইকুয়েশন 1 এর জন্য।
This is for this is line 1, this is line 2. This region, this yellow colored region is for line 1. This green colored region is for line 2. Understood?
Thank you, sir.
Someone, one student was saying something. He's saying the common feasible region to thakbei. Not necessarily. Common feasible, you are dealing with a problem where you cannot have a common, you may not have a common feasible region at all. Now the question is, if we don't get a common feasible region, how can I interpret the solution? That is what I am asking right now. So if you can get a problem where after modeling it, you find that no, it doesn't have a common feasible region, so you will say that no, you cannot optimize the given objective function. Understand? In question number 8, if I change the given problem to minimization type, suppose I'm writing it as minimization, same thing, and the rest of the things remain same, what will be the answer for question number 8? Tell me.
Sir, can you repeat the question?
Same question. Instead of maximize, I am writing minimize.
Same answer. Same answer.
Same answer, sir. We don't have any.
So no,
Common region.
We don't have any common feasible region.
no solution. No solution. Okay, so this is not changing. Means previously what we saw that with respect to maximization type and minimization type, the problems were changing. Previously, if in case of maximization type and minimization type, the problems were actually changing. But here, the problems are not changing. The problems are remaining same. But both the problems are, the solution are not changing. The solution is remaining same because of no common feasibility. No common feasibility. In the previous case, since common feasible region was there, so therefore different solutions we obtained. Now, have you understood it? Do you have any doubt regarding this, what I have discussed so far?
No, sir.
Okay.
No, sir.
Now the thing is that I'm going to give you a problem. Yes.
What is the use of this one, that z equal
What?
to 2x 1
Yes.
and x2?
Yes. What? I've not understood.
It is a constant in the diagram. Z
এটা দিয়ে তো
equal to
ম্যাক্সিমাম
2x
মিনিমাম
1.
পয়েন্টটা বের করছি।
Z is the objective function.
Oh, okay.
Z is the objective function. When we found in the previous case, this was the function where we substituted the value of x1 and x2 to find these values. This Z gives you either the maximum value or the minimum value. There may be some problems I cannot recall right now. There may be some problems also where you can find for two different points. It could have been much better if I could show you, but I'm unable to find a suitable problem right now. It can so have, which I'm writing here is a point. In some problem, it is a note actually. Right now, I don't have any problem of that sort in my hand. In some problem, it may so happen that for two different points, for two different set of points, say x1, y1 and x2, y2, we get same maximized or minimized value of the objective function. We can get such a problem where you are getting two different points, corner points, for which the same value or same maximized value or same minimized value are coming for two different points. Such a solution is actually called multiple optimal solution. Multiple optimal solution. Understood? But right now I cannot give you any such example because I do not have such example with me right now. I cannot recall. You just keep this in mind. Sometimes it may so happen that you have got such a situation and you are thinking that, oh my God, there are two different points are existing and same maximum value is coming. So what shall I write? Which point should I consider? This or that? You have to consider both of them. You'll say this is the solution, one solution, that is the another solution, both giving same minimum value or both giving same maximum value. Now I'm giving you a problem. So you just take it down.
স্যার একবার আগের পেজটা একবার যাবেন স্যার, স্ক্রিনশটটা তুলুন।
Yes. I don't like to write questions.
Thank you, sir.
Big questions on the classroom because it takes time, lots of time. So, but since I have not created any WhatsApp group, so if I can create a WhatsApp group with you, then in that case, I will, in advance, I will share the question with you, and that question will be discussed. So that is the objective. Other objectives are also there. You'll be happy to see. I will show you once the group is created. But now, right now, I'm taking the pain of writing this big question. The manager of an oil refinery must decide on the optimal mix of two possible two possible blending processes. I hope I can finish writing this question in this session, of which the inputs and outputs per production run are as follows. We have this chart with us. Two types of processes are there, 1 and 2. Input in input section. In input section, there are two types. One is crude A, another is crude B, crude oil type of thing, crude oil. So this is 5 units, 4 units, 3 units, 5 units. And output section, we have two types. One is gasoline. From crude oil, they are creating gasoline X type and gasoline Y type. And 5 units are there, 4 units are there, 8 units are there, 4 units are there. Now, the maximum amounts available, of crudes A and B are 200 units and 150 units respectively. Market requirements show at least 100 units of gasoline X and 80 units. Quickly take the screenshot of gasoline Y. Otherwise, I cannot repeat it in the next session. Must be produced. The profits per production run from process 1 and process 2 are rupees 300 and rupees 400 respectively. Take screenshot. Quickly formulate LPP. Quickly take the screenshot.